Hi, I'm Ashley and I'm going to be speaking about ultrasound Doppler today. What is Doppler? We've all experienced Doppler without realizing it. Here's a brief example of what a Doppler shift would sound like. Doppler shift is also called Doppler frequency, and this happens as the source of sound and the receiver change distances. It has a direct impact on the Doppler frequency as they are directly related. This shift is measurable and we use it in the body to measure blood and blood flow, blood velocities. The Doppler shift is measured in hertz. One equation is reflected frequency subtracting transmitted frequency. Frequency shift. A positive Doppler shift happens when the blood is moving towards the transducer. A negative Doppler shift happens when blood is moving away from the transducer. Velocity is a measure of speed and direction. Doppler shift is directly related to velocity. It's also directly related to the transducer frequency. Another equation that we use to calculate Doppler shift is 2 times the velocity of blood times the transducer frequency times the cosine of the angle. This is all divided by the propagation speed. The sound beam direction and flow direction. They're 100% accurate when the sound beam is parallel to the moving blood cells, but the human body is not always parallel and we're not always able to get that parallel angle. So when these angles do exist, the velocity is not the true velocity. The cosine of the angle accounts for this discrepancy. A percentage of the true velocity is measured, and we use the equation of measured velocity equals true velocity times the cosine of the angle. The Doppler shift and the cosine of the angle are directly related, and what happens to one happens to the other. One doubles, so does the other. The angle of the blood flow at 0 and 180 degrees is parallel, so the measured and true velocities are equal. A positive cosine indicates blood flowing towards the transducer, and a negative cosine indicates blood flowing away. We can't measure Doppler shifts at perpendicular incidence. The machine cannot determine the direction of flow when we are perpendicular. So we measure at 60 degrees, and this gives us half of the true velocity. And this is also reproducible by other sonographers on repeat exams. Pulse wave Doppler is another form of Doppler that we use in ultrasound. With this type of Doppler, an exact spot can be picked to measure exact velocities. It is also called range resolution, range specificity, freedom from range ambiguity artifact, and we place a gate or sample volume. This is the marker for where we measure. Here on the right side of the screen are 2 examples of different sizes of gates, and both have impacts on why we would choose to have different sizes in ultrasound. A smaller 2mm range gate is going to give a smaller sample of volume velocity measurements. The larger 10mm range gate is going to give a larger sample volume of the entire vessel. That's also why we see differences on the graphs below. Aliasing is the most common error that occurs with Doppler ultrasound. High velocity flow is displayed incorrectly. These velocities go to the very top of the spectrum and wrap back around and are displayed incorrectly on the bottom. The top of the spectral display is referred to as the Nyquist limit. The portion displayed incorrectly on the bottom is referred to as aliasing. To fix, we raise the Nyquist limit or we reduce the Doppler shift. So just a little bit more about aliasing and ways that we can avoid it. less aliasing occurs with slower blood velocities, lower frequency transducers, a shallow gate or higher pulse repetition frequency. More aliasing is going to occur with faster blood velocities, a higher frequency transducer, and a deep gate or low pulse repetition frequency. Some tips to avoid aliasing are we can move the scale to its maximum, we can find a new sample volume that is shallower, we can switch to a lower frequency transducer, we can shift the baseline, or we can use continuous wave Doppler. Color flow Doppler. Color Doppler displays average or mean velocities. It displays the direction of flow. A color map is located on the right-hand side of this screen and also on ultrasound display screens. This can be one of two separate maps. The first is a velocity map or mode. This displays flow direction and velocity. The middle black line indicates there's no Doppler shift occurring. Above the black line shows that blood is moving towards the transducer. Below the black line indicates that blood is moving away from the transducer. The second map is a variance map or mode. This adds more information than the velocity mode. It distinguishes between laminar and turbulent flow. The left side of this map indicates laminar flow. The right side is turbulent. When we see this, we should think there's some sort of pathology and investigate further. The colors are not always consistent and can be inverted, so we just need to remember that top is towards the transducer and bottom is away. This image is just one way in which color Doppler is used in ultrasound. This image is an image of the liver, and it's showing the different directions and velocity variations of blood flow within that liver. We also use it for other things as well. We look for blood flow within veins and arteries to check if there's any sort of plaque buildup, if there are clots. We can also use what is known as twinkle artifact to look for stones in gallbladders, kidneys, and there are many other uses for Doppler in ultrasound as well. This was just a brief summary of some of the ways in which we use Doppler in ultrasound. Thank you so much for taking the time to listen to my presentation, and have a great rest of your day.